So let's look at Lyapunov theory. A nonlinear dynamic system can usually be represented by a set of nonlinear differential equations of this type. F is a n by 1 nonlinear vector function and x is an n by 1 state vector. So a particular value of state vector is also called a point because it corresponds to a point in the state space. The number of states n, so the dimension of the vector space in which the system is lying, is also called the order of the system. A nonlinear system 3.1 is said to be autonomous if f does not explicitly depend upon time. That is, if the system's state equation can be written in this form, x dot equal to fx. If time explicitly enters the function f, then it is said to be a non-autonomous system. Let's look at a definition. A state x star is an equilibrium point or an equilibrium state of the system. If once xt equals x star, it remains equal to x star for all future time. Mathematically, this means that the constant x star satisfies the equation f of x star equal to 0. So basically, we have equated to 0 this equation and solve for it. The autonomous equation, and solve for x. And we get the equilibrium states. This is the pendulum. This is the governing differential equation of the pendulum, of the simple pendulum. It has a mass, oscillating mass of capital M. Its length is equal to r, and theta is the angle the string of the pendulum makes with the vertical axis. Upon applying the Newton-Euler equation to the system, we get this governing differential equation. When theta is small and there is no damping B at the hinge, this system undergoes a simple harmonic motion. When theta is large, the approximation sin theta equal to theta is not possible when theta is large, and therefore this has a periodic motion but not a simple harmonic motion. It's a harmonic motion but not simple harmonic. Now, the equilibrium point x equal to 0 is called stable if for any r positive there exists a little r positive such that norm x0 less than r implies norm of xt is less than capital R for all t positive. Otherwise, the equilibrium point is said to be unstable. So if we look at this diagram, take any capital R, the dotted circle is the capital R, and corresponding to that, there must exist a small r for any capital R. This should happen. So even if there is one combination, one capital R for which there is no small r, such that this condition is true, then the equilibrium point is unstable. Okay, so this should be true for any capital R. The any is important, of course. Now in this example, we see. Now let's look at the van der Pol oscillator. This is a state space representation of the van der Pol oscillator. This is the phase portrait of the van der Pol oscillator. So isoclines have been used for graphically plotting these phase portrait. The van der Pol oscillator has a limit cycle oscillation. The closed trajectory shown in bold in this phase portrait is the limit cycle of the van der Pol oscillator. If we look at any initial condition inside in the interior region of the limit cycle, the trajectories expand and land on the limit cycle. If we look at the trajectories outside of the limit cycle, they converge down and end up on the limit cycle itself. So the trajectories inside as well as outside of the limit cycle land on the limit cycle. So the limit cycle is stable, as we'll see shortly. However, if we look back at the equations, x1 dot, x2 dot, and if I look for the equilibrium points of the system, it is easy to see that origin is the equilibrium point, because substituting x1 equal to 0 and x2 equal to 0, we have 0 on the right hand side. So the origin is an equilibrium point. Now, if I take for capital R to test the equilibrium, the stability of this equilibrium point, we apply this definition. And see if for any r there is a small r such that the initial condition inside small r implies future course inside capital R. is it true? Or is there a combination, is there a capital R for which there is no small r, such that this statement is true? So it turns out that if I take the capital R to be lying inside the circle, there is no small r, because every trajectory which starts from the origin always lands on the limit cycle. So as seen in the phase portrait, system trajectories started from any non-zero initial states all asymptotically approach the limit cycle. This implies that if we choose r to be small enough for the circle of radius capital R to fall completely within the closed curve of the limit cycle, then the system trajectory starting near the origin will eventually get out of this limit cycle. So this implies that the origin is unstable. So an equilibrium point is said to be asymptotically stable if it is stable and if it in addition satisfies the following condition. There must exist a capital R, small r, such that initial condition inside small r implies the xt, the time course, the future course of x, goes to 0 as t goes to infinity. An equilibrium point which is Lyapunov stable but not asymptotically stable is called marginally stable. So an equilibrium point which is Lyapunov stable but not asymptotically stable is called marginally stable. In many applications, it is still not sufficient to show that a system will converge to the equilibrium point in finite time. There is a need to estimate how fast the system trajectories approach 0. And the concept of exponential stability can be used for this purpose. So an equilibrium point 0 is exponentially stable if there exist two strictly positive numbers, alpha and lambda, such that x of t's norm is less than or equal to alpha times e to the minus lambda t into norm of initial condition in some ball of radius r around the origin. So exponential stability is of course initial asymptotic stability, because if t goes to 0, t goes to infinity, xt goes to 0. If asymptotic or exponential stability holds for any initial state, the equilibrium point is said to be asymptotically or exponentially stable in the large. It is also called globally asymptotically stable. Let's look at the first order system, x dot equal to minus x plus x squared with this initial condition. Its linearization about the equilibrium point is x dot equal to minus x. The solution of this linear equation is exponential e to the minus t. So we look at a graph of the solution of the linearized equation as well as solution of the original equation. Now the original equation can also be integrated, and the solution, the actual response of the system, is found to be this by integration, as it is a variables separable system, both the given equation as well as the linearized system. So we look at the responses of linearized system as well as the original system, and we see that the original system is actually diverging in a neighborhood of 1, whereas the linearized system is having convergent trajectories. Let's look at the procedure of linearization and talk about local stability. We have the autonomous system x dot equal to fx, which can be linearized to produce a matrix equation of this type, x dot equal to ax, where a is obtained in this fashion. It's called the linearization or linear approximation of the original nonlinear system at the equilibrium point x equal to 0. Now, a controlled system x dot equal to f of xu can also be linearized, and we may obtain a matrix equation of the type x dot equal to ax plus bu after doing the linearization of the f as well as f is a function of x and u. So applying these suitable derivatives, computing the suitable Jacobians, it is possible to get the A and B matrices as shown here. Now, this example shows how to linearize the system. So this is a nonlinear system on the right hand side. Now we linearize about 0. So upon linearizing, applying the Taylor series, we have this matrix equation is the linearized system.